So let's talk about a few more things before we get into some fun stuff. So let's say we have XP. XP is a particular solution. So we're starting with a non-homogeneous system. Non-homogeneous means AX is equal to some B vector and we don't have all zeros there. Then that means that every solution can be written in the form of x equals xp, which is the particular solution, plus the solution xh, which is the homogeneous solution. So let's look at an example. Let's look at 9. We want to find the set of all solutions. Notice that this is a non-homogeneous system. We know it's non-homogeneous because it's not equal to a whole bunch of zeros. So let's solve this system. So to solve this system, we have 1x1, 0x2, minus 2x3, plus x4 is equal to 5. 3x1 plus x2 minus 5x3 is equal to 8. x1 plus x2 minus 5x4 is equal to negative 9. So if we do RREF, so this is saying x1 is equal to 2x3 minus x4 plus 5. x2 is equal to negative x3 plus 3x4 minus 7. And x3 and x4 are free. So what this is saying is we can take this solution and we can write it in terms of xp plus xh. So xp is your particular solution. Particular solution consists of just numbers. 5, negative 7, and then 0, 0 for this, because we could assume this is plus 0 and then plus 0 here. So xh would be the solution of the homogeneous system. And I'm going to rewrite this in a minute. So we could rewrite this way. So I'm grouping those x3 terms together. And then I'm grouping the x4 terms together. So there's our solution. Now, I want to prove to you that this is the actual solution for the homogeneous system. I'm telling you it is, but I want to show you. So you're technically solving two systems in one here. If we were to solve this system where it's homogeneous, here's our augmented matrix. Now, I want you to compare this matrix to above. I'm going to zoom out a little bit so you can see that. Do you see how this guy is identical to this guy? The only difference is what's on this side. If we were to do a Gaussian elimination on all of these zeros, 0 with any operation added to it, if we have a whole bunch of zeros, will still end up being zeros. So when we do RREF, we're going to get that same matrix on the left and then just zeros on the right. You should take a minute, pause the video, and then verify that. You'll see that's kind of a neat thing that happened here. Oops, that should be a 0. So there's my RREF for that homogeneous system. So then our system is going to look the same. x1 is equal to 2x3 minus x4. x2 is equal to negative x3 plus 3x4. Both x3 and x4 are free variables. So if we were to write that out here, you'll see that guy here. So you can see how it is that homogeneous solution to that. So that's pretty cool. Let's look at example 10. Let's consider this system of equations. Now, before that, we have theorem 419. Let's read what that says. We have solutions of a system of linear equations. The system AX equals B is consistent if and only if B is in the column space of A. So consistent means that we have either one solution or an infinite number of solutions. So if we can write B as a linear combination of the vectors of the column space, then we know we're going to have a consistent system. So let's look at this guy. If we were to take this, plug it into an augmented matrix. This is what I got out. So if we think about what this means, we have 3 equations, 3 unknowns, and we ended up with a row of zeros here. This means we have 2 planes and they're intersecting on a line. So the equation of that line is the solution to this system. There's an infinite number of solutions here. But because there is at least one solution, then we have a consistent system. So this says x1 is equal to 3 minus x3. x2 is equal to negative 4 plus 2x3. And x3 can be anything. So in 3 dimensions, this is the equation of a line. Now, what this theorem is saying is that because this is consistent, we could take this B matrix and write it as a linear combination of the column space of A. So what is the column space of A? So we're going to find those leading ones, and we're going to use that first column and that second column of the original matrix. So there they are. So there's my column space, 113 and 102. So because this is a consistent system, we're guaranteeing that we can write that column, that B column, in terms of those 2 vectors. So let's try it. So I'm going to recopy the column space, and then this is our B matrix, and we're going to come up with what that would look like. So we're saying that C1 times that first vector plus C2 times that second vector is equal to our B matrix. So we have C1 plus C2 is equal to -1. C1 plus 0C2 is equal to 3. 3C1 plus 2C2 is equal to 1. So we know what C1 is. This is an overdefined system. We have 3 equations and 2 unknowns. So let's plug that in here. So 3 plus C2 has to equal -1. That means C2 is equal to -4. And since it's overdefined, we have to check it here. So 3 times 3 plus 2 times -4, is that equal to 1? 9 minus 8 is equal to 1, so it checks out. So then we can write B. So then B, which is this matrix, is equal to 3 times that first vector minus 4 times the second vector. So that's all that theorem is trying to say. So like we said before, we're building this set of criteria where everything's an equivalent statement, or equivalent conditions rather, for square matrices. So let's look at where we're at so far in that build. So if A is an n by n square matrix, then the following conditions are going to be equivalent. So if A is invertible, then that means that we have to have a unique solution for AX equals B. Remember, unique means that there has to be one solution. And since there's one solution for that, then that means that AX equals 0 must only have one solution, and that solution is the trivial solution. Remember, for homogeneous systems, you could have either one or an infinite number of solutions. This is guaranteeing us one, all because A is invertible. Now, that also means if we were to do row operations on that coefficient matrix, we're going to get something that's row equivalent to the identity matrix. That also means that if we're equivalent to the identity matrix, A is invertible, and all this other stuff holds true, then the determinant of that matrix, that coefficient matrix, cannot be 0. That's one way we checked for invertibility, was by looking at the determinant of the matrix. And if we know that, we know something about the rank. Here's where we're adding new stuff. The rank of A has to be equal to n. And it has to be equal to n because we're row equivalent to that identity matrix. So when we do RREF, let's say we're a 2 by 2, then we're going to get that. So there's our rows. And that leads us to talking about independence of the row vectors. That means we have n row vectors of A that are linearly independent. So if we're talking about 2 by 2, we're going to have 2 rows that are independent. 3 by 3s would have 3 that are linearly independent, and so on. And if we have n row vectors that are linearly independent, then we're going to have n in the row space, n vectors in the row space. That means we're going to have n vectors in the column space. So we're going to have n vectors that are linearly independent in columns as well. So you can see how all this is starting to build. So it's kind of cool to think about all of that in linear. So the last thing we're going to talk about is orthogonality. And this is going to be really big a little bit later into the course, but we're going to start introducing this idea now. So we say two vectors are orthogonal if their dot product is equal to 0. So if you remember how to find a dot product, and we're talking about the Euclidean inner product. This is your standard dot product definition. So if U is vector U1, U2 to UN, and V is vector V1, V2 to Vn, then to dot those, U dot V is going to multiply those, add, multiply those, add, and so on. So that's your definition of that dot product. So if that dot product happens to be 0, then they're orthogonal. So if W is a vector space of Rn, then the set of all vectors in Rn that are orthogonal to every vector in W is called the orthogonal complement of W. And notice the notation we're using here. We're using that perpendicular notation, and that is a superscript on W. So now we're going to start talking about complements and what does it mean to be an orthogonal complement of a vector space. So if W is a subspace of Rn, then the orthogonal complement of W is also going to be a subspace of Rn. There's only going to be one vector that's common to both of those, and that's going to be the 0 vector. And then the orthogonal complement of W, I'm not sure how to say that without saying orthogonal complement. So the orthogonal complement of the complement of W is W itself. So what that's saying mathematically and math speak is that if I take the complement of the complement, I'm going to get back to W. So what we're going to focus on right now is what if I have a matrix? So if A is an m by n matrix, then the null space and the row space end up being orthogonal complements. And the null space of A transpose and the comb space of A are going to be orthogonal complements of each other. So I just want to do an example to kind of illustrate that. And like I said, we're going to talk more about orthogonality later. But let's just talk about one of these right now. Let's say our matrix A is this matrix. So we need the row of A and we need the null space of A. So I'm going to find the REF form. So the row space of A ends up being these two vectors. Now let's talk about the null space. To solve the null space, you set this equal to 0. And when we perform row operations, we're going to get 0. So our null space is going to be x1 equals negative x3 plus 2x4. x2 is equal to x3 minus 2x4. So x3 is free. x4 is free. So if I group x3 together, from that first line, I'm going to have a negative 1 if I factor x3 out. I'm going to have a 1 from the second line, 1 from the third one, and then I don't have an x3 here, so it's understood to be 0 x3. Plus x4, 2, negative 2, 0, and 1. So then our null space consists of those two vectors. So what this is saying is that they're orthogonal complements of each other. So I'm going to call this V1, V2, V3, and then V4. So if I were to take V1 and dot it with V3, 1 times negative 1 plus 0 times 1 plus 1 times 1 plus negative 2 times 0. That's going to give me 0. And if I dot V2 with V4, I'm going to get 0. Anytime you get that dot product to be 0, that means you're dealing with an orthogonal set. So in this case, this set is orthogonal to this set. So now let's look at the null space of A transpose and the column space of A. So we can find the column space pretty easily. We've already done RREF up here. We need to identify the leading ones here and here. So we're looking at first column, and we're looking at second column. So there's our column space. Now let's look at the null space of A transpose. So A transpose, let me make this smaller so I can see my A. There's my A transpose. Let's do RREF. Remember, you're going to have to trick your calculator into doing this. So I ended up with this. And remember, we're looking for null space. So we really need this to be AX equals 0, which would give me this. So now I know x1 is equal to 2x3. I know x2 is equal to 0. x3 has to be real. So then my null space consists of the vector 2, 0, 1. That's your coefficients of x3. So I'm going to call this v1, v2, v3. So just to show that orthogonality, if I dot v1 with v3, I'm going to get 1 times 2 plus 0 times 0 plus negative 2 times 1. And I see I get 0. And if I dot v2 with v3, I'm going to get 0 also. So we're showing that they're orthogonal. So right now in this section, I just really want to focus on the orthogonal complements here. That's important to me. Like I said, orthogonality is going to come up later. There are ways you can force things to be orthogonal, and we'll talk about something called the Gram-Schmidt process when we do that. So you can see our equivalent statements are now building. So take some time and read through those. And we'll meet up again in the next section.